Hello, this is Linear Regression Lecture 3, continuation of multiple linear regression. In the first part of the multiple linear regression lecture, we discussed the basics of conducting multiple linear regression and the concept or idea that you have one dependent variable but multiple independent variables work into the same equation. We also discussed in that part of the lecture the concept of multi-collinearity, the fact that different independent variables may influence each other, which could potentially distort the quality or the goodness of our regression model. One of the things that we mentioned in discussing linear regression through both simple and multiple linear regression was the variables that we were using were numeric in nature. The data was interval type data, which means numeric. We used things like time, size, distance, and so forth. We also used money. But very often when we do research, especially when we're doing descriptive research, which is sort of a hybrid, where we use surveys, we collect data that's not numeric in nature. For example, we might ask a person whether they're male or female. We might ask them the state in which they live. And so this nominal characterization of data values is called categorical variables. Now, we haven't discussed yet how we would incorporate an independent variable of male or female, or state, or region, or any other categorical variable into our regression model as an independent variable. And so the remainder of the lecture discusses how to create and use substitute variables in the place of the categorical variables. The typical way we refer to these substitute variables is dummy variables. And so let's discuss a situation where we might have categorical data that's not numeric, and how we would adjust our regression model to accommodate the categorical variables. So we'll begin with an example. We'll discuss the idea of being able to determine house prices in neighborhoods. And so you can see in this example that on the right-hand side, we've included our spreadsheet data, which I set up for us. It only has 18 of the first 50 observations showing. And we're trying to support an analyst who develops house pricing models for local realtors. The objective is to analyze whether the quality of the local high school impacts the price, and whether the location by region, we'll use region to keep it simple, and whether the location of the home in terms of the region, northwest, east, or south, impacts the home price. So what is it that we're trying to focus on? The main thing, it's the price of the house. So that's our dependent variable. And then we've got two other factors we want to ask ourselves: to what extent do these other factors influence the price of the house, our dependent variable? And so the high school quality will be independent variable 1, and the region or the location of the home will be independent variable 2. So we're trying to predict the price. We're trying to examine high school quality and region and how they influence the home price. I've set the data up in the spreadsheet. My dependent variable is in the first column this time. It's listed as price, and you can see my observations, at least the first 18. There's more. I've hid those, but there's actually 50 total observations, and the average home price is $181,212, the average of all 50 observations. I included square feet, which is also sometimes an indicator of home price for all 50 homes. And so the observations of square feet have an average of 1,772 square feet. Then we structured the data, the additional data, the exemplary high school, the quality high school is either yes or no. That's my X1. And again, you can see the yes, no's in column C. Note that there's no way to average yes and no's. But what I did do at the bottom is I did a count. I counted the number of the number of no's is 27, and the number of yeses is 23. So you can see we've got the data fairly evenly split between those homes located in an area with a good high school and those homes located in an area with a not so good high school. And then we have region, and I categorize region as north, south, east, or west. And so our X2 region, you can see our categorical data is N's and W's and S's and E's. And so, again, you can't average categorical data, but what I did do was I did a count of 16 homes in the east, 11 homes in the south, 11 of the homes are in the west, and 12 of the homes are in the north, for a total of 50 homes. So again, you can see that there's a fairly evenly distributed spread with a slight bias towards the number of homes in the east, or 16 of those. So that's the data that we would like to analyze. So the question is, how would you do a regression analysis? If you tried to do a regression analysis, even a simple regression, comparing the price to the exemplary high school, the statistical tool is going to say to you that one of your variables is not quantitative, and therefore you can't do a regression on it. And so we need a way to deal with this. So the way to deal with this, and I'll give you the rules in a second, is to create additional columns in the spreadsheet. So what I did was I copied the price and the square footage over into two columns K and L, and then I created a surrogate column, a dummy variable column for exemplary high school. Since exemplary high school has only two different values, a yes and a no, I only need one column, and I'll explain that in a second. And so I create this new column called exemplary high school, but instead of using Y's and N's or yes and no's, I use numbers because we need numbers to do regression analysis. So I've converted the yeses to ones and the zeros to no. Now, a couple of things to note. One of the things I did back here under column C is at the very bottom, I decided that no would be equal to yes, and I documented this, and that yes would be equal to 1, so that when I start my coding in this column here, that I am clear and that I remember and I don't get confused about what my variables are. You might think that's pretty simple and not necessary, but once you get to 4 variables, and you'll see in a second, my east, south, west, and north need to be converted, I need to be a little more clear about that. So we'll talk about that in a second. So you can see in column M, I now have a new set of values for exemplary high school being 1s and 0s. Notice that at the bottom, the count of the number zeros is still 27, and you can see how I did that at the bottom. I show you the Excel macro. And the count of yeses is still 23. So I actually still counted my zeros and ones to make sure I didn't miscode something. If in fact these numbers were different than they were here in column C, that would suggest that I put some 0 or some 1 in the wrong place. Now, again, without having reviewed the rules, we'll review the rules next. I needed to turn the region into numeric data as well. And the way you do that, and I'll give you the details on this in a second, is you decide on one of the 4 values. First, you note that it has 4 different values. Then the next thing you know when you create dummy variables is that one of the values is not going to need an extra column. That's going to be called your anchor variable. And so I selected east, and that's the E equals 0 at the bottom, to be my anchor column, or my anchor value in this column. And so, and I'll explain this again, so don't let this trip you up. So because I've selected east as the starting point, I don't need a new column for east. However, I do need a new column for all of the other categorical variables. So note that there's 4 different variable values here in region, right? The north, the south, the east, and the west. Since I picked the east to be my anchor, I don't need the east. That means I still need 3 more. So you can sort of figure when you have more than 2 values, whether it's 3, 4, 5, or 6, that you're going to have to create columns for all of the values except 1. So the first thing to do when you're thinking about dummy variables, if you have more than 2 values in your column, is you're going to know that once you count up how many different values you have, and at the bottom it tells me that I have 4 different values, that means I'm going to need 3 more dummy variables. Okay, I don't need to include the anchor, but I do need to include the rest of the dummy variables. So when you look here at columns N and O and P, note that there's no east column. That's because I've selected east as my anchor. Now what I need to do, once I set up my south column, and I call that X3, my west column I call it X4, and my north column I call it X5, once I've set these up, what I need to do is to go through and convert each observation. So the first observation in row 4 was north. So south is 0, west is 0, and north is set to 1. Okay, the same thing is true for the next 2 columns, next 2 rows. The next 2 rows. They're both north, so the 1 is in the north area. In the 4th row down, I've got a 1 in the west column because that value is W. Then I've got 5 souths, so you see the 5 ones in the south, and I set the others to 0. Now you can't have a situation where you have a 1 in the south and a 1 in the west. That's just not, that would not be correct, and your regression attempt would give you an error message. So notice as you go down the columns that you have zeros and ones in all the columns. Now what happens when we get to a value of east? And I have to go all the way to my bottom example here in row 21. Well, it's not south because it's east, that's 0. It's not the west because it's the east, that's 0. And it's not the north, so that's 0. And so the fact that I have 0, 0, 0 here means that this is the anchor variable value. And so anytime you see 3 zeros across your 3 dummy variables, you know that that's the referring back to the east. Okay, now I'll give you the details of this in a second. The other thing I did was I did a count. I counted how many 1s I have in the south column, and I came up with 11. And then I came back over to my original numbers where I had south as 11. Then I counted the west, and I got 11, and I came over and checked, and the west was 11. Then I counted the north, and the north was 12. And if you do the math, you would know that 11 plus 11 plus 12 minus 50 gives you 16. So by default, I knew that I had 16 values in the east. And so I can see that I've double-checked my observations totals here, compared it back to my original observation totals, went back when it was letters. And again, I'll show you how to do these counts here at the bottom. You can see my count if S statement at the bottom. That's how I did these counts. Okay, so I hope that's clear, but let's see if we have a little narrative to explain that, and that's coming up soon. Now, the next thing that I needed to do once I came up with my dummy variables is I need to go back and do my individual regressions. So I decided to do a regression of size, square feet, and price. Remember when I first set up the data, I said it'd be interesting to see if there's a correlation between size and price. And so I ran a simple regression on those 2 variables. I got a p-value of less than 0.0001. And that tells you that these are very, very significantly correlated. And you can see below that the line is almost straight with a few outliers here. And so that tells me that including, since I'm focused on the price of the house, including size as one of the variables is not a good idea, even though because they're so closely correlated, it really wouldn't tell me anything. I now wanted to do a comparison between my new dummy variable exemplary high school and price. And so I selected the column that had the 1s and 0s in it for exemplary high school. Then I selected the price column, and I ran my regression And I've got some very good correlations here. So this is a good independent variable to use because I have very low p-value, and I have reasonable R-squares. They're not great R-squares. And so because of this p-value, I know that using exemplary high school to predict price is a reasonable thing to do. I then compared the high school and the region and the price. I compared all of the variables using the dummy variable columns. And when I did this, I got the following regression data, and I analyzed it. First, I looked at my R-square and adjusted R-square, and I can see that the high school and the region where the home is located can account for 62%, 63% of the total price determination of the house. So I thought that was a reasonable expectation. You know, there's certainly other things that dictate the price of a house, but having a quality high school and being located in a certain region is very important. I also came and looked at the sum of the squares, but in reality, when you're dealing with ones and zeros, when you're dummy variables, you really don't have useful data in terms of trying to use the sum of the square of the errors, because your data points are all ones and zeros. So if you ever do a scatter plot, you're going to just see straight lines because the values you've converted them to ones and zeros. So your yes and no is going to be you've scattered around either 0 or 1. And the same thing will be true with your region. They're going to be scattered across 4 different lines representing north, south, east, and west. So the sum of squares is not useful to you when you're using dummy variables. I looked at the individual p-values, and I noticed that I've got good p-values for the constant, which is the independent variable, and then I've got good p-values for south, north, west, and north. So the p-values are pretty good. So I've got a significant model. I've got a constant coefficient, if you look here under the coefficients for the regression table, of 221,091. And what that tells you is that's the y-intercept price of the homes in my model of 221,000. That's the base price that I work with. Then when I look to see whether the high school is going to affect the home price or not, I note that when the high school is a 1, when there's a quality high school, that adds $5,982 to the $221,000 price of the house. So the house with a good high school is worth about $6,000 more. And then I looked at my coefficients from our regions. Now notice that the east region is not here. Now that's important because what you're seeing here is that the constant coefficient of 221,091 is the price of a house in the east region. So by omitting the anchor variable, when you calculate your regression with dummy variables, your constant value is representative of the value in the anchor variable value, in this case in the east region. Okay, so now what it says here is that if I try to price a house in the south region, I need to take $83,483 off the price of the $221,000 house. What it's saying is in the south, houses are worth $83,000 less because it's got a negative sign. In the west, houses are worth $43,544 less. And in the north, houses are worth $61,190 less than the value of the house in the east region. And this is consistent. This is consistent with the data that I set up, because I actually did have the east region as being the highest priced houses and the houses that are closest to good high schools. And so this does match sort of the way the data was arranged. And so again, I've got a predictive model here. So what's the important thing to keep in mind? One is that I've converted the categorical variables into dummy variables. I converted all of my non-quantitative data into quantitative data by creating these columns of ones and zeros. Second thing to appreciate is that when I do this and I have more than two values in any column, I'm going to have one of them designated as the anchor. And when the regression is created, this constant value here is going to represent that anchor or omitted column. And so that's important. And so then everything else is considered in reference to the anchor value, and that's what the constant represents. So I hope that's somewhat clear. In terms of creating the dummy variables, here's the rules that I was trying to cover earlier. One is when you have categorical data, your observations have to be converted to ones and zeros. This example in this slide here is talking about when your categorical data only has two values, yes, no, male, female, and so on. When this is the case, and you only have two values, you're going to create one dummy variable column only. So in the example we had, exempt high school was categorical, but it only had two values. I look at the values in the observations, and there's only two. So I only need to create one representative column. And in that representative column, I need to convert the yeses to ones, and I made that choice, and the nos to zero. And so there's my conversion there. And so this would be true if it was true or false. If it was female or male, you would convert it whichever way you'd like to convert it. If the data said hired or not hired, it's only two values, yes or no, then you would be hired equal 1, not hired equal 0, where you can reverse them if you'd like. And so that's how we create a dummy variable when our independent variable only has two different values. Okay, and then again, as I discussed before, if you have more than two values, north, south, east, or west, small, medium, or large, age bracket, you can think of many situations where you'd have more than one choice on the survey question for a person. You know, select from one of the following four, select from one of the following three. Occupation is another example. And so in the case where you have more than two values for your independent variable, you need to first go through the column and figure out how many different values you have. Okay, and then the second thing you need to do is you need to create dummy variables, dummy variable columns, dummy variables for the different values less 1, because the 1 is going to be your anchor. So what this slide says is categorical variables with more than two values. One of the values will serve as anchor or the reference value. You'll see it referred to sometimes as anchor, sometimes as reference. You'll always have one less dummy variable column than the number of values. And so in that case, if you have 4, you're going to need 3 dummy variables. If you have 3 different values, you're going to need 2 dummy variable columns. If you have 5 values, you're going to need 4 dummy variable columns. And then you make the choice. Just be sure to document which of the values, when you're setting this up, is going to be your anchor, because you need to code your values correctly using the zeros and ones. So you create a new dummy variable column for all values except the anchor value. In the case of 3 values, small, medium, and large, designate small as the anchor, and then create 2 new dummy variable columns for medium and large. If you have 4 values, north, south, east, and west, you designate north as your anchor, and you create 3 new dummy variable columns for east, south, and west. And so you can see an example over here. On the right-hand side, I wanted to convert garment size, medium, small, and large, 3 values, 3 different values being small, medium, and large. Therefore, I need 2 dummy variable columns. So I pick small as my anchor, so I create a column for medium and a column for large. When I start filling out these columns, the medium gets a 1 in the medium column and 0 in the large. I get a small value, I get 0 for medium and 0 for large. The small by default is all zeros because that's my anchor. And so you can always tell an anchor value when you look across your dummy variable columns, because your anchor value has all zeros representing the categorical data. So I hope that's reasonably clear. It's just something that you have to feel comfortable with. There is a feature in Stat Tools where you can actually have Stat Tools create dummy variables. And so you would, in this case, if you're using that feature in Stat Tools, you would select the garment size column, and it would create, surprisingly, it would create 3 dummy variable columns. It would actually create a column for small, and it would have values in that column. However, when you go to run the regression multiple regression analysis using Stat Tools on the data, it would say that you have 3 different values, and you're trying to run it with 3 different columns. And so it would force you to come back and only use 2 of the 3 columns. So there's no way that you can ever run a regression with an actual defined base value. You can't do it. Just FYI. Okay, so how do we interpret the regression results when we have more than 2 values? I already went through this once, but I'll show it to you again. When you have a two value categorical variable like a yes/no, the coefficient represents the change in the dependent variable if the independent variable is positive. Okay, so in the example to the right here, you can see that this is the price we were just looking at. That the price of the house is $155,700 in this particular example, where I was only looking at high school. And you can see that the coefficient that I received back for exemplary high school was 55,460. And so what this tells us is that in the neighborhoods with an exemplary high school, I can add a $55,000 premium to the price of the house, making the house worth $210,000 if the high school is exemplary. Now, remember back from the example a few minutes ago, the premium was only $5,000. And the reason that was the case was because we had introduced east, south, north, and west as well. So we introduced more variables, and we changed the characteristic of exemplary high school as a predictive variable. Okay, now we can't see the R squared here, but if you look at the R squared here, you can see the R squared is quite low, saying that the exemplary high school really is a small predictor of the price of the house, and that sort of explains the difference. But this shows you how you would read a regression output if you have a categorical variable like the exemplary high school. So you would see the constant reflecting the price, the independent variable value, the dependent variable value price, 155,700, and you would see the coefficient of the dummy variable, the exemplary high school, as being 55,460. Now let's take a look at how we would interpret the table, and I went through this before. If we have all of our categorical variables included, and I mentioned this before, but this gives you the slide to actually reinforce what I was saying to you before, that the coefficients here in the regression table really are interpreted as in reference to the anchor variable. And so the constant reflects the price of the house, the estimated price of the house, 221,091, in the east region, in the anchor variable region. The exemplary high school, yes, no, accounts for about $6,000 of the change in price. In other words, if there's an exemplary high school located near the house is worth $227,000 instead of $221,000, holding everything else constant. Now, if we start to look at the which region the house is located in, we know that in the east region it's 221,091. So holding the high school constant, not including that change there, as we mentioned before, we note that in the south region the house is worth 83,000 less. In the west region, 43,000 less, and in the north region, 61,000 less. So we have our basic model. You can't see the regression equation here at the bottom. I sort of cut that off a little bit. Yeah, sorry about that. But basically it says that y hat is equal to 221,091 plus 581 times x1, the first independent variable, minus 83,482 x2, which is the next independent variable, minus 433,544 x3, third independent variable, and minus 61,190 x4, which is the fourth independent variable. So this regression equation here, which got a little bit cut off, is used as a predictive model, and it's a very useful thing. Okay, so I hope that was clear. There were certain points when I was talking about things where I thought that it wasn't as clear as it needed to be, but I'm hoping that you can see when you have categorical data, you have to convert the data into dummy variables. It's not hard to do if your categorical variable only has two values, because then you just create a 1 and 0 column for it. It gets a little more complicated when your independent variable has more than two values, because you have to convert, you have to pick one as a base value and not create a column for it. And then for the rest of the values, you have to create additional dummy variable columns and include the ones and the zeros. If you do that, you're going to run your regression analysis. You're going to get a constant coefficient that represents the value for the variable that you selected as your base variable, and so then the rest of the variables have to be adjusted based on their coefficients. So key points from lecture 3 overall: multiple linear regression has one dependent variable and more than one independent variable. It explains more of the dependent variable variation because you added more explanatory variables. And so it's a little more powerful than simple linear regression. But we also note that sometimes just willy-nilly throwing independent variables into a model can create problems. They can create overfitting, and they can create multicollinearity. And multicollinearity often is caused by having two independent variables that basically do the same thing. And that also creates some distortion in the model. And so when we think about reducing multicollinearity, we're looking for variables that have about the same effect on the model, that they have a strong correlation to each other, and we want to take one out if we can. If the relationship between the two independent variables suggests some multicollinearity, but not a lot of strength of relationship, then you have to make a decision as to whether you leave them both in or not. We talked about how to run and interpret regression output. It's a little different than simple linear regression because you have more coefficients to deal with. Also, you have this potential for multicollinearity. And then finally, we talked about how to deal with categorical values using dummy variables. And so categorical values, the nominal type data, yes, no, male, female, tall, short, and so on, the non-numeric data had to be converted into numeric data through dummy variable process. And the dummy variable process always converts categorical data into a series of ones and zeros. If your variable only has two different values, you create one dummy variable column, and you identify one value with a 1 and the other value with a 0, and it's fairly simple. If your variable, as you look down the column, has more than two values, you need to pick one as your anchor value, the reference value, and then you need to add a column for the rest of the values. And so you can see my note at the bottom here. It says if you have three different values as you look down the column, you're going to need two dummy variable columns. If as you look down the column you see four different values, you're going to pick one of them to be your anchor, and you're going to create three additional dummy variable columns. When you do this, you run your regression. You run the regression on the dummy variable columns, not the categorical variable columns. And what you're going to wind up with is an output that you can interpret reasonably well. Remember, when you're using dummy variables, that the sum squares the error doesn't make a lot of sense. Also remember that the value that you get, the coefficient for the constant, which is your dependent variable, is a representative of the anchor value, and then the other values that you created adjust up or down relative to the anchor value. And we went over that in detail. And so I hope this has been a useful lecture and a useful introduction to simple and multiple linear regression. There are going to be other lectures, other YouTube lectures on statistics. One that is planned is on forecasting methods. It's not done yet. Also, a series of lectures on more basic statistics, t-test, chi-square analysis of variance, correlation, and just some of the more basic concepts. So those will be included as well as time permits. End of lecture. Hope you enjoyed it. Dr. Kessler out.